beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. The past and the future, the ultimate vacation destinations. But are they within reach?
They could happen within a few years or a few decades.
When you travel through time, strange things start to happen.
You can imagine warping things so dramatically that you can actually visit yourself in the past.
Some humans have already made the trip.
You will have jumped into the future while aging very little. That's really cool.
See how it's possible as we unravel the mystery of time travel. Of all the riddles of the universe, time travel may be the most perplexing.
Time itself has a lot of fascination for us, and so we end up thinking of ways of cheating time and things like that, going back in time, changing things.
Time travel could involve going back in time or speeding into the future. But for the moment, every one of us is frozen in the present. Yet science holds out the possibility that we might loosen the hold that time has on us. Einstein's theory of relativity, in which time plays a central role, makes time travel an open question.
Our best theory of time, which is relativity, doesn't explicitly forbid time travel per se. It might be that there are things we yet don't understand that will improve the theory. But it seems that there are ways of constructing scenarios within relativity that allow you to go back in time.
Traveling into the past seems improbable because time only goes one way, forward. Physicists call this the arrow of time.
The arrow of time is just the fact that you can always orient yourself moving from the past to the future. You remember the past, you don't remember the future. You can cause things to happen in the future, but you can't cause things to happen in the past. If you took a movie of things going on in your everyday life, like mixing cream into your coffee, and then you played that movie backwards, it would be perfectly obvious. Cream mixes into coffee, it doesn't unmix. That's the arrow of time.
The arrow makes time a one-way street of irreversible events, something we know intuitively from our everyday experience. On a pool table, you can break, but don't expect the balls to realign on their own. You can scramble an egg, but you can't unscramble it. The reason why time has an arrow is a fundamental law of physics that says all things in the universe move from orderly states to disorderly states.
As the universe gets older, as we move from the past to the future, all of the differences between the past and the future can be summed up by saying that the universe is winding down. The universe is going from being orderly, very neatly arranged, to disorderly and messy. So if you had a plate that was a nice plate that was put together and orderly, it breaks, it becomes more disorderly. That's very natural.
And if you try to restore order by gluing the plate back together, your actions release enough energy into the surrounding environment to create more disorder in the universe as a whole. But the arrow of time can be bent in extreme conditions. It all goes back to Einstein's theory of relativity. Einstein showed that the gravity of massive objects like planets, stars, black holes can actually cause space itself to bend. More amazing than that, he showed that space and time are actually linked into a single something he called space-time. This means that whenever space is warped, so is time. And nothing in the universe can bend space-time more than the supergravity of a black hole.
So you can imagine the gravitational field is so strong that space and time curl back on themselves. And you can start at one point, go forward in time, and come back at the point that you left.
When the arrow of time bends around to meet its tail, it creates an endless loop in which the same events happen over and over.
So if this is time curling back on itself, and the universe just repeats itself over and over again, every moment in time would just repeat an infinite number of times.
An endless loop would become pretty frustrating for anyone. But suppose a time traveler can land in the past without the constant repetition. In that case, there are other roadblocks. The most perplexing are the inconsistencies or paradoxes that pop up when we start meddling with the past.
A famous example of the kind of inconsistency you can get with time travel is called the grandfather paradox. And this is where someone goes back to the time of, for example, their grandfather. So imagine that I go back in time with a time machine and meet my grandfather in 1937. He's just about to go on a blind date with my grandmother. They've never met before. But actually, I convince him not to go on that date. He's actually interested in the races, and so I tell him that there's an exciting race with Seabiscuit that's coming up at the Santa Anita track. And so we go off together to that race. He never meets my grandmother. So what happens to me? How is it possible that I could have been born and then been able to go back in time, meet him, and stop myself from being born? So there's an example of an inconsistency. It's a loop in time that really doesn't make sense.
But if time travel is possible, nature must have a way around the contradiction.
One thing that physicists are quite certain of is that the universe ultimately makes sense.
In all of physics and all of science more generally, consistency, self-consistency, common sense, if you like, is something that is a fundamental principle.
Physicists have come up with at least 3 ways that nature might act to prevent time travel paradoxes. The first is simple. Nature prevents paradoxes by making time travel into the past impossible. In other words, it can't be done. A different alternative is the strange idea of multiple universes.
One way of dealing with travel back in time is to say that you actually enter a different parallel universe after having made the journey back in time. So you don't affect the history of the universe from which you came. In effect, anything that can happen will happen. But the way it happens is by entering a parallel universe. Pretty bizarre thought.
A third solution to the paradox problem is the notion that if time travel is possible, you just won't be able to change the past when you get there. The science behind this can be illustrated by reducing the problem to the simplest situation you can think of. For example, balls on a pool table.
Let's set up a pool table that's like a time machine. If a ball enters one pocket, it travels through a wormhole and can exit another pocket before it entered the first pocket. So it's a time machine. So now suppose the ball really does go through the first pocket, emerges before it entered, and then hits itself before it entered the first pocket. That would deflect it, preventing it from entering the first pocket, and thus preventing it from having exited the second pocket and done the deflection in the first place. So it's a paradox. However, the idea of self-consistent solutions gives us a way out of this paradox. Suppose that the ball exiting the second pocket can only hit itself in such a way as to deflect it into the first pocket. Then the whole loop is self-consistent. There's no paradox. We think that nature always somehow manages to choose the solution that provides self-consistency. In other words, you always get a solution that does not produce a paradox.
If that's the case, and Clifford Johnson were able to travel to the year 1937, he might be able to meet his grandfather. But despite his best efforts, nothing he does would alter the fact that somehow his grandfather will meet his grandmother to allow Clifford to be born. One way or another, the universe will prevent him from changing history. But we don't have to worry about paradoxes when we travel forward, taking the arrow of time into the future.
Traveling forward in time is the easiest thing in the world. Every minute, you move 1 minute forward in time.
One thing we can do to change how we move forward in time relative to each other is to actually move at different velocities compared to each other.
A time machine that takes us into the future is based on Einstein's discovery about time and speed. The faster you move in space, time, for you, slows down as compared to people standing still. And as mind-bending as this seems, it's actually been proven by experiments.
Clocks have been placed on rapidly moving airplanes and rocket ships, and they've moved over some distance at a very rapid speed. And when the atomic clocks were measured after the end of the journey, they had progressed forward in time a little bit less than similar clocks which had remained at rest on Earth.
The effect is called time dilation, and we can use it to travel into the future. In fact, it's already been done. Russian cosmonaut Sergei Krikalev has logged more than 803 days in orbit, traveling 17,000 miles an hour, making him the world's record holder in time travel. Though you'd hardly know it to look at him.
What's actually happened is that he's about a 50th of a second slower in the amount of time that has passed for him compared to everyone else who stayed on Earth.
But dilation really begins to pay off as a time machine when you pump your speed to just under the speed of light. The idea is to let clocks on Earth move at their normal speed, while you're off in space, and your clock is moving more slowly. When you get back, you're in the future. Suppose, for example, you wanted to go 500 years into the future.
To move 500 years into the future, you'd have to move at 99.99% of the speed of light for 7 years.
When you get back, you'll have aged only 7 years. But everything on Earth will have aged 500. But one of the biggest problems with building a time machine for travel into the future is finding enough fuel to boost a spaceship to speeds that high.
There's no law of physics that says you can't go close to the speed of light, but your rocket ship becomes heavier and heavier as you go closer and closer to light speed. So you require more and more fuel to accelerate you smaller and smaller amounts. And you need more than an infinite amount of energy to actually break the light speed barrier.
But high speed isn't the only way to zip into the future. Einstein's theory of relativity says high gravity also slows down your clock. The kind of gravity you might find near a black hole.
Let's say you're in a spaceship and you go and you park yourself just outside a black hole for a while. Once you return to Earth, you will notice that many, many years may have passed on Earth, but only a few weeks or months will have passed in your own frame of reference. You will have jumped into the future while aging very little. That's really cool.
But spending years at high speed or near a black hole is a slow kind of time travel. For more impatient voyagers, there may be an instantaneous version by way of a shortcut through space called a wormhole that could also become a corridor through time. To conquer time travel, we have to tread a long path that takes us through bizarre theories and incredibly complex technology toward a goal that will one day make starships into time machines. Starships, in fact, may be our best bet. We shoot off in a rocket ship at super speed and let our own time slow down while the rest of the world moves on. We have a vested interest in these kinds of adventures. The high speeds that result in time travel are also our only way of smashing a time barrier that keeps us from traveling to the stars, because the distances are so huge.
We would really like to be able to traverse giant distances in a short amount of time in order to explore the universe on a human timescale.
Even the nearest stars to Earth seem impossibly far away. Alpha Centauri is the closest. But in this case, close amounts to 4.3 light years away, 25 trillion miles. 100 million times farther than the moon. Today's speediest rockets would need 80,000 years to get there, so the challenge is to get there faster. But if we're going to use high-speed star missions as our way to get to the future, it still doesn't satisfy our dream of getting there in a flash.
Achieving time travel by moving fast and so slowing your clock down relative to everyone else is a way of achieving time travel. It's a little bit like Rip Van Winkle did by going to sleep and then waking up later and it's the future. But some might think of that as cheating in a way. It's not really the time travel that we think of, where we perhaps go through a portal or flick a lever on a machine and then end up at a different time.
Physicists did important theoretical work on instantaneous time travel in the 1980s, while helping Carl Sagan, who was writing his novel, Contact. The book imagined space travel faster than light through a corridor in space called a wormhole.
A wormhole is a kind of shortcut between two different parts of space, which can be very far away, or they can actually be close to each other. But the key idea is that you can traverse the wormhole by simply going in through the entrance, one side of it, and coming out the other side.
In Contact and many other science fiction scenarios, wormholes are used as tunnels to travel huge distances across the universe to other stars. But a wormhole with openings close together is a much better starting point for a time machine.
Suppose I have a wormhole right next to me. If I put my arm into it like this, it would emerge over there. A wormhole is a great ingredient for constructing a time machine.
A wormhole time machine would use the same Rip Van Winkle trick as the very fast spaceship. Super speed makes your clock slow down, while everyone else keeps on going. It works because both ends of the wormhole always have the same date and time, no matter what happens to them.
You can take one end of the wormhole and put it on a rocket ship or something and send it off at very high speed and then back. So what happens is that when it returns, it's in the future.
A traveling wormhole opening from the year 2010 might end up returning to Earth in the year 2510. Because its clock was so slow, it aged very little, while the rest of the world aged 500 years.
So now if I walk into the end of the wormhole that's in the past, the end that didn't go on the rocket ship, I can come out the other end and I'd be in the future. Although each step of this scenario might be really hard to achieve with any technology we can imagine, it's all internally consistent in the laws of gravity and space and time that we understand so far. So that wormhole time machine is, we would say, a consistent solution of the equations of space and time.
The wormhole time machine would work in reverse, too, making time travel theoretically possible from the future back into the past, where you started.
Well, let's face it, most people are interested in the idea of going backwards in time because they want to fix things. The interesting thing is, though, that we can, using the laws of physics, at least explore what it would be like to travel backwards in time.
And although we're preoccupied with time machines, it may be that time travel is possible through wormholes that are natural in origin.
Another possibility, if we can't make time machines, is that maybe nature has already made them, and we just have to discover them. What could have happened is that in the very early universe, the nature of space and time was already twisted up in such a way that some of that got frozen in, leaving time loops that we might be able to use as time machines sometime in the future. So it's an interesting possibility that we don't actually have to create these things.
But what if we are left to our own resources? Can we build a time machine at all? If theory says a wormhole is the way to go, then what does it take to make one?
Wormholes are speculative ideas. We can write down the equations that describe them. We don't expect to bump into one in astronomy or anything like that, but we could be surprised. Where we do expect wormholes to exist is at the sub-microscopic level, where space and time are fluctuating wildly. So what people imagine is somehow capturing a microscopic wormhole and growing it to a larger size. We don't know if that's possible. We have no idea how to do that, but that's probably what it would take if you wanted a big-sized wormhole.
The technology we need to manipulate a wormhole may seem impossibly remote. But for those willing to let their imaginations roam, there's a glimmer of hope in at least one place. It's where space, time, the nature of existence itself meet in head-on collisions inside the biggest, most complex machine ever created by man. Where does the universe hide the secrets that might tell us how to travel in time? Our exploration has taken us through the world of wormholes and their possibilities as time machines. And now we're in search of the technology that might make space travel and time travel two sides of the same coin. If there's nothing on Earth that comes close to being a time machine now, there is something that might one day lead us to new laws of physics that help us determine if it's at least possible. It explores the universe not in the realm of the cosmic web and its galaxies, but in the domain of quantum physics, involving particles at sizes more than 1,000,000 times smaller than the smallest atom. It's the newest tool at the frontier of physics called the Large Hadron Collider.
The Large Hadron Collider is the largest, most complicated machine ever created by humankind. And its role is to help us study the frontier of particle physics. What it actually does is it accelerates protons in two directions around the ring, one way round and the other way round, to nearly the speed of light, and then collides them.
The collider went operational in November 2009. And as scientists ramped up the power, the energy in its collisions was increased almost tenfold by March 2010. And it will double that sometime after 2013. Today's theories of space, time, gravity, and quantum physics are still incomplete. And tools like the Large Hadron Collider will help fill in the ever-puzzling blanks.
This is where we expect that if there's some missing physics that we need to understand space-time in a way that will tell us whether time travel is possible or restricted in various ways, this is where we expect the new results to come from.
The goal is to figure out how rules governing the tiniest particles in existence also apply to the biggest things, like stars, galaxies, and the expanding universe itself. Without understanding this, building a time machine might be harder than trying to build a radio without knowing about the existence of electricity.
There are many physicists in the world who believe that this understanding is in fact right around the corner, that it could happen within a few years or a few decades. On the other hand, it could be that this problem is in fact much harder than we think, and that human civilization will simply not live long enough to figure out how it works.
The Large Hadron Collider might also reveal extra dimensions that could play a role in time travel. We live in 3 dimensions of space. If we lived in only 2 dimensions, our universe would be a flat sheet. A sphere would look like a circle to us. The 3rd dimension would be there, but just hidden from our view. If dimensions other than our familiar 3 are really there, they too are hidden.
If we were to find experimental evidence for the existence of other dimensions, and if we were to be able to explore the meaning of these other dimensions and see how they come about, it could be that far, far in the future, this new physics would be utilized to come up with some new form of travel that allows us to at least get close to the speed of light barrier, if not surpass it.
Getting close to light speed may be the most promising way to travel in time by slowing down our clocks. In this respect, the Large Hadron Collider is leading the way, even if its first step is an extremely small one.
The Large Hadron Collider is 17 miles around, and it accelerates protons to nearly the speed of light. If you wanted to do that, but with human beings, a rough calculation shows you'd have to scale it up to 1,000 light years around in order to do the same thing.
This is like saying that the spacecraft powerful enough to carry us to the stars at that speed would be bigger than the distance we need to travel. Big enough, in fact, to enclose the nearest 100,000 stars. Back on Earth, the physics of light speed and beyond meets surf culture on the beach in Malibu, California. Richard Obusi is one of the few physicists who have worked on the concept of faster-than-light warp drive. A warp ship, he says, rides a wave-like ripple of warped space, almost as a surfer rides a wave of water.
A great analogy is with that of a surfer riding a wave of seawater. So just as the wave behind it sort of rises up and pushes this surfer through the ocean, I think that's a great analogy with how a spacecraft is mutually pulled and pushed through the fabric of space.
The idea is based in part on the fact that space in the universe is expanding. If we can make it expand at will, we may be able to propel a warp ship. We make space expand behind the ship and make it contract in front. The wave of warped space moves through the universe faster than light, while inside a so-called warp bubble, the ship is a passenger, never violating Einstein's rule against exceeding the speed of light. While warp drive is mostly science fiction at this point, there is some physics behind it. Mexican physicist Miguel Alcubierre worked out the complex math to support it in 1994. Unfortunately, there's nothing in the math that tells us how to do it. And though most scientists have major doubts, not all the skeptics are writing off warp drive completely. Warp bubbles may be impossible, they say. But what about super advanced beings building faster-than-light warp-drive bullet trains to the stars and through time? In searching for the secrets of time travel, we inevitably meet the idea of warp drive. or other strategies for traveling faster than light. It's the most sought-after solution to the dream of star travel, and potentially turning any spaceship into a time machine. The most optimistic views of the future paint a picture of spaceships riding warp bubbles as easily as expert surfers catch waves off the beaches of Earth. But even optimistic physicists must face some harsh realities. If surfing is an analogy for how a warp ship might work, then watching a beginning surfer drives home a better point. Achieving warp drive is very difficult.
This morning, I had my first surfing lesson and had this idea that in some sense we were going to be able to manipulate in some sense nature, and that I was going to be able to ride this wave, and it was going to carry me at great velocities across the ocean. But the reality is that the ocean manipulated me. It was far harder to control than I originally anticipated.
And control is a real problem, because science says a warp ship just can't make its own warp field.
One of the often cited problems with the warp drive model is the ship would be what we call causally disconnected from the bubble. That is, it could never find a way to communicate with the bubble, and so could never turn the bubble off once it had started.
But what would happen if the starship did not have to worry about turning its bubble on and off?
What you might imagine for a sufficiently advanced civilization and given sufficient new laws of physics would be some kind of warp drive escalator or corridor. And then when you would drop a ship into the prearranged warp tube, if you will, it might be able to ride some wave along to the end.
It would be like a bullet train to the stars. Its passenger cars might travel faster than light. But whoever invents it would need thousands of years at sublight speeds to build it and use more energy than we can imagine.
We would probably need to harness at least the energy output of an entire star, if not a lot more than that. So these are things we can talk about hypothetically, but no one has an engineering program to make it happen.
When astronomers recently discovered that the expansion of the universe is accelerating, they reasoned it was driven by a mysterious dark energy that is part of space everywhere. A few people have suggested that dark energy can be harnessed as a power source for exotic devices like starships or time machines.
We don't really know what the dark energy is, so it's not clear that we will never be able to harness it. However, the leading models suggest that it's either a property of space itself that can't be changed, or some sort of an energy field which is of such low density, there's so little of it per unit volume, that harnessing interesting amounts of it will essentially be impossible.
The bottom line when it comes to warp drives, wormholes, or time machines leads many scientists to reject them out of hand. Can we be sure that they're right?
Though we think we know a lot about the universe right now, and we do, there have been many times in the history of physics when we've been burned by having too much of a self-assured sense of knowing it all.
There really are laws of physics that we can't violate. But there's also technology. You say, well, this is just too hard, we'll never be able to do it. And there, when scientists say things like that, they're almost always wrong. It's much safer for us to say, here are what the laws of physics allow us to imagine doing. Hopefully someday in the future, we'll build the technology that makes it happen.
And as we've seen, that future may confront us very soon, as astronomers search for planets around stars outside the solar system. The closest star system to Earth has a binary pair of stars. Is that a good place to search for planets? That's just what Nicole of Oklahoma City, Oklahoma, wanted to ask the universe when she wrote, "Can planets exist in a binary star system?"
Nicole, that's a really cool question. It turns out that a planet in a binary system can orbit either one of the two stars very closely, or it can orbit both of them from very far away, but it can't orbit among them. It can't do a figure eight among them, for example. That trajectory is unstable, and the planet would quickly get ejected.
We may be on the verge of discovering an Earth-sized planet around one of the two stars in the Alpha Centauri system, the Sun's nearest neighbor. It would be a more compelling reason than ever before to explore the exotic science of high-speed space voyages and the time travel that goes with them.
Alpha Centauri is very exciting because it now appears from a variety of different computer simulations that it's quite possible that there could be terrestrial mass planets orbiting both components of the Alpha Centauri binary system.
Alpha Centauri A and B are so distant they look like a single star from Earth. But they're actually a binary pair. A third member of the system is Proxima Centauri, a red dwarf loosely bound to the main pair.
If you're sitting on a planet in the Alpha Centauri A system or the Alpha Centauri B system, Proxima Centauri wouldn't even be visible in your night sky. It's that dim.
Alpha Centauri A and B orbit around each other. At their closest point, they're about 20% farther than the distance from the Sun to Saturn. At their farthest, they're 20% more distant than the Sun is from Neptune. Each has a habitable zone similar to the Sun, where life-bearing planets could exist. And that, after all, is a holy grail in astronomy.
Well, a trip to the nearest stars, for example, Alpha Centauri, that we can do within our lifetimes would be immensely exciting. One of the great goals of science is to find life elsewhere in the universe. What better place to start, other than our solar system, than the nearest star?
But now, space travel becomes time travel, as we set our sights on a mission that can be done under the laws of physics we know now. A mission that can cross more than 4 light years of space in just 45 days. Our quest to unravel the mysteries of time now point us again to Alpha Centauri, the Sun's closest neighbor. It is the most likely first destination for a starship from Earth. A starship whose mission cannot avoid a component of time travel.
We have no idea what kind of technology would actually take us from here to Alpha Centauri and back. Therefore, we might as well be optimistic and say that we just move at 99.99% the speed of light all the way there and then all the way back.
The ship seems surprisingly small for one that has to make such a long trip. How can it hold enough supplies to support a crew for the duration? It can because it is not only a starship, it is also a time machine.
It would take about 8.6 years because Alpha Centauri is 4.3 light years away. But to the people on the ship, it would take less than 2 months. It would take about 45 days because they're traveling close to the speed of light.
The astronauts would also have to overcome the problem of killer acceleration in quickly reaching the speed of light. Otherwise, they'd have to speed up slowly, adding time to the total trip. Alpha Centauri is the go-to destination for Earthbound beings hoping for a toehold in star travel. It's no accident that James Cameron chose it as home to his fictional moon Pandora in the movie Avatar. The reason we would go to Alpha Centauri has to do with today's intensive telescope search for Earth-like planets around Alpha Centauri B, one of 2 stars in the system's main binary pair.
Alpha Centauri B, it turns out, is by far the best star in the entire sky. for searching for low-mass Earth-like planets. But to carry out that kind of search requires a very dedicated effort. It's not something that you can accomplish in a few nights at a telescope.
It's hard enough to separate the two main stars of Alpha Centauri in a space photograph. Trying to see an Earth-sized planet around one of them is, at the moment, impossible. The best shot we have is to find the planet by the wobble method, detecting a star's subtle back and forth motion caused by the tiny gravitational tug any planet would have on it. Like time travel, it seems almost undoable.
The back and forth wobble that we need to detect is incredibly small. I'm here at the Rose Bowl, and if the Rose Bowl were the size of Alpha Centauri, then the amount of wobble that we need to detect is about this much, about 3.3 inches. And we need to detect that from 4.3 million miles away.
Alpha Centauri b is slightly smaller than A, and the planet hunt is concentrated there, mostly because a smaller star will show more wobble and detection will be that much easier. In 3 to 5 years, we should have an answer.
I think that if we were to discover that there's an Earth-mass planet orbiting the very nearest star, then there would be a great deal of excitement to somehow either build a large telescope to try to observe that planet, or perhaps in the far future to design a mission that could actually go there.
With the goal of our time travel quest identified, we can imagine our spacecraft in Earth orbit about to leave on the first mission to Alpha Centauri. The ship's high speed propels it into time machine mode, slowing its clock so its passengers approach Alpha Centauri in 3 to 4 weeks. Seeing things up close no human has ever seen before. First up, a stellar flare from the red dwarf Proxima Centauri. On the outskirts of the triple system, it is the closest of the three to the Sun.
Proxima Centauri is prone to these sudden outbursts that can cause it to brighten up by a factor of 4 or 5 over the course of just a day and then fade back just as quickly. So you might be in for some real fireworks as you pass by Proxima Centauri.
As we come within the triple star system, we might imagine swinging past Alpha Centauri A and using gravity assist to send us in a direction of Alpha Centauri B.
The sister Earth of the ship's destination is the ultimate goal, and the travelers will be anxious to explore it and search for life. Although the trip has taken little more than a few months for the travelers, the high speed will slow down their clocks so much that when they return, nearly a decade will have passed on Earth. The realization of star travel at high speed is a dream for the far future. On an Earth where technology is so advanced and changing so fast, the difference of 8 or 10 years could be dramatic. This kind of time travel may become routine to a new generation of star travelers. Taking mankind on the next giant leap in its epic journey through the universe.